Hello everyone. So today we'll start with the numericals on losses in pre-stress. I think in the last lecture we have already completed the basic theory about the losses in pre-stress, the various losses in pre-stress and the various equations involved in it. So today we'll actually start with the problems. So let's start with the problem. A pretensioned beam of a rectangular cross-section 150 mm wide and 300 mm deep is pre-stressed by 8 wires of 7 mm diameter located at 100 mm from the soffit of the beam. Soffit means bottom of the beam. If the wires are initially tensioned to a stress of 1100 Newton per mm square, calculate their stress at transfer and the effective stress after all the losses given the following data. So what is the data given to you? The relaxation of steel is given to you at two stages. First is up to the time of transfer and then the total. So relaxation of steel up to the time of transfer is 35 and total is 70. Shrinkage of concrete is 100 into 10 raised to minus 6 and total is 300 into 10 raised to minus 6. Creep coefficient up to time of transfer is it's not given. For total it is 1.6 and modulus of elasticity of steel and concrete are given to you. So basically what they're asking in the question, we have to find out stress at transfer and the effective stress after all the losses. So first let us write down the given data which is given in the question. So basically the first thing which is given to you is the dimension of the section. So we'll draw that section, cross section. It is 150 by 300 mm overall and 8 wires of 7 mm diameter is the steel and it is at 100 mm from the soffit of the beam. Soffit means bottom of the beam. So as you can see in the figure, I have shown the wires which are at 100 mm. And what else is given to us? Initial stress is given. I have written Fi is 1100 Newton per mm square and Es is 210, Ec is 31.5 and phi, that is creep coefficient, is also given to you, that is 1.6. So based on this we can find out the modular ratio, which we already know is nothing but modulus of elasticity of steel upon modulus of elasticity of concrete, so which comes out to be 6.67. So from the cross section you can understand the various data which is given to you, and eccentricity is nothing but it is the distance from the neutral axis to the CG of the steel. So that you can get from the figure. It comes out to be 50 mm because half is 150, so 150 minus 100 is nothing but 50 mm. I hope you understood that. So that is the given data, and next we have to find out two things. First is stress at transfer and effective stress after all the losses. So this is what we have to find out. So let us start with the solution. So okay, so the first step is we'll start with the finding out the section properties. So section properties will find out the area first. So area is B into D, which comes out to be 45 into 10 raised to 3 mm square, and moment of inertia of the section is BD cube by 12, so that comes out to be 33.75 into 10 raised to 7 mm raised to 4. So the section properties we got. So now what else is given to us? Actually the area of steel is also given to us, so we can find out area of steel is nothing, area of wires is 8 number of wires and the diameter is 7, so 8 into pi by 4 into 7 square, that comes out to be 308 mm square. Okay, so we got the area of wires also. So now what we'll find out, we'll find out the initial pre-stressing force. So once you have the area and the stress, so you can definitely find out the force. So force is nothing but stress into area. So initial stress is 1100, area of steel is 308, so the initial pre-stressing force we got is 333.8 kilonewton. So now we will find out what is the stress in concrete at the level of steel. So we have discussed this in the previous lecture. Fc is given by P by A plus P square upon I. So we have the value of P, we have the value of A, we know the eccentricity, which is nothing but 50 mm, and we have also the value of moment of inertia I. So from that we got the value of Fc as 10 Newton per mm square. So now these are the basic values which we got. Now we can actually go to find out the first part of the question, that is to find out the stress at transfer. So to find out the stress at transfer, we'll find out all the losses. So the first data which is given to us is loss due to relaxation. So we will find out loss due to relaxation, which is given to us. As you can see, I'll just go through the previous slide. Loss due to loss of steel, relaxation of steel is given as 35 Newton per mm square. So we have written 35, it is directly given to us. Then loss due to elastic deformation. So loss due to elastic deformation is nothing but m into fc. We already know the formula. So m is your modular ratio, which we have found out as 6.67, and your fc is 10, so that comes out to be 66.7 Newton per mm square. So next we'll find out loss due to shrinkage. So loss due to shrinkage is given by shrinkage strain into modulus of elasticity of steel. So shrinkage strain value, we will take what is given in the question. First we are trying to find out up to the time of transfer, so it is given as 100 into 10 raised to 6. So 100 into 10 raised to minus 6 into 210, it is given in kilonewton, so we have just converted that into Newton, so multiplied by 10 raised to 3. So we got the value of loss due to shrinkage as 21 Newton per mm square. So the total loss is nothing but the addition of all these three losses. So loss due to relaxation, loss due to elastic deformation, and loss due to shrinkage. Okay, so remember, we'll find out the losses which is actually given to us in the question. Okay, so that is the reason we found out loss due to relaxation, loss due to elastic deformation, and loss due to shrinkage. So now stress in steel at transfer is given by initial stress minus losses. So we already know what is the initial stress, that is 1100, and this loss, total losses we got is 122.7. So this is the stress, total stress in steel at transfer, which is 977.3 Newton per mm square. So I hope you understood the first part of the question. Now we'll find out the second part of the question. So for the second part, we have to find out the effective stress in steel after all the losses. So for this, we will take the data which is given in the question, loss due to relaxation, which is given in the question. I'll just show. So as you can see here, loss due to relaxation total is 70. Similarly, shrinkage of concrete, we have 300 into 10 raised to minus 6, and creep coefficient as 1.6. So we'll use that data. So loss due to relaxation is 70, which is already given. Loss due to shrinkage is shrinkage strain into modulus of elasticity. Shrinkage strain is given beyond the transfer is 300 into 10 raised to 6 minus 6. And loss due to elastic deformation is m into fc, which remains the same as we got. And loss due to creep of concrete, since creep data is given to you in the question, we will also find loss due to creep of concrete, that is 5 into m into fc, which comes out to be 106.72. so therefore we'll find out the total losses by adding all the four losses, so that comes out to be 306.42 Newton per mm square. So now effective stress in steel after all the losses is initial stress minus losses, which comes out to be 793.58 Newton per mm square. So I hope you understood this problem. So I have done it very systematically in a stepwise manner so that you understand it, and we have solved the first problem. So now let us go for the second problem, which is, so let me read out the second problem for you. A prestressed concrete pile 250 mm square contains 60 pre-tensioned wires, each of which 2 mm diameter, uniformly distributed over the section. The wires are initially tensioned on pre-stressing bed with a force of 300 kilonewton. Calculate the final stresses in concrete and percentage loss of stress in steel after all the losses given the following data. So let us see what is given in the question. So it is given that it's a 250 mm square pile. So I've just drawn that cross section, and it contains 60 pre-tensioned wires. So you can see that it is throughout the pile. So these wires are throughout the pile, as you can see in the figure, 60 wires of 2 mm diameter. Total force given is 300 kilonewton. Modulus of elasticity of steel and concrete is given to you. And what else data is given? Shortening due to creep is given to you, 30 into 10 raised to minus 6. Total shrinkage is given to you, 200 into 10 raised to minus 6. Relaxation of steel stress is 5% of the initial stress. Pre-stressing force 300 kilonewton, and area of the steel wires is also given to you, which comes out to be 188.5. Okay, so this is the given data. So what we have to find out, so again there are two parts in the question. First we'll find out the final stress in concrete. So as it is asked in the question, to find out the final stress in concrete, and the second thing they've asked is to find out the percentage loss in steel. So let us start with the solution. So as per the given data, we will find out the unknowns accordingly. So area of steel wires is given to us. So based on that, we can find out the initial stress Fi is nothing but force upon area. So initial force we know, and area of steel is also known. So initial stress Fy is 1591.51. Okay, so we got the initial stress. So now the second thing, we have been given the value of ES and AC, so we can find out modular ratio, so which comes out to be 6.56. So next we'll find out FC, that is stress in concrete at the level of steel, is given by P by A plus P square upon I. So since we can see that the steel wires are uniformly distributed all over the section, so we can ignore the second term, that is P square upon I. So your FC will become P by A. So that comes out to be 4.8 Newton per mm square. Okay, so now we can actually find out the various losses. So first we'll start with loss due to creep of concrete. So loss due to creep of concrete is given by epsilon cc into fc into es. So it is given in the question. Your shortening due to creep is given in the question, so that's the reason we have used this formula. So we have two formulas basically to find out loss due to creep. One is phi into m into fc, the other one is epsilon cc into fc into es. So I told you we have to use the formula accordingly as per the given data. So we have used this formula and we got the value as 30.24. So next we'll find out loss due to shrinkage. So loss due to shrinkage is again shrinkage strain into modulus of elasticity. So shrinkage strain is also given to you, as you can see, 200 into 10 raised to minus 6. So we got loss due to shrinkage. Next we'll find out loss due to relaxation. So loss due to relaxation is 5% of the initial stress. Initial stress is nothing but 1591.51. So we got loss due to relaxation as 79.58. So next we'll find out loss due to elastic deformation. We have the value of M, we also have the value of FC. So we got loss due to elastic deformation as 31.49. So now the total loss is nothing but the addition of all these losses, which comes out to be 183.31. So once you got the total losses, so now can you find out the effective pre-stress? So effective pre-stress is nothing but the initial stress minus losses. That's what we found out in the previous question. So the effective pre-stress is initial stress is 1591.51 minus the losses is this. So we got the effective pre-stress as 1408.2 Newton per mm square. So now with the help of this effective pre-stress, can you find out the effective force? Yes, we can. So effective force is given by effective pre-stress into area of the steel. So effective pre-stress we already got. So that gives us the value of effective force after all the losses, which comes out to be 265.45 kilonewton. So now what is the first part of the question? The first part of the question is to find out the final stress in concrete. So the final stress in concrete is nothing but the effective force upon the area of the section. So effective force we got as 265.45 kilonewton, and area is of the section is nothing but 250 by 250. So that comes out to be 4.25 Newton per mm square. And the next part of the question is to find out the percentage loss in steel. So percentage loss of stress in steel is nothing but the total loss upon initial stress into 100. So total loss is 183.31 and initial stress is 1591.51 into 100 gives the value of 11.517 percentage. So that was the second question. So I hope you understood the solution and all the steps. So two parts, the final stress and the percentage loss in steel we got. So this in this lecture we have seen two questions. So in the coming lecture, I'll again take one more problem on losses, and then we can move on to the next topic, that is analysis of the beam sections. So I hope you understood this lecture, and both the numericals are pretty much simple.